I'm still super excited that I can tell you about my research through this. Since I've how do I advance my slides? What is, there we go. Yeah, since I have no idea who is in the audience or only a slide idea from the program, I thought I'd quickly introduce myself, who I am. So I'm running a small group at Princeton Chemistry. This is a bit of an outdated group picture right here of us. And while we're a group in the chemistry department, we're very interested in problems related to condensed matter physics, and these involve new topological materials and also new two-dimensional materials. But I will be mostly talking about this issue, this first topic today. And because we're chemists, we have a very different way of thinking about material science in general, but also in relation to topology in particular. And so this is just a slide where I put up my group logo, where I say that while chemistry and physics might think about things differently, there's actually a lot of common ground at the interface between these two halves of the brain, where we can find new science if we learn how to speak each other's languages. And so a large part of this talk is actually starting to bridge this language gap, and then trying to explain what kind of new physics we can envision once we understand each other. And I want to start with a definition of topological matter, which is extremely simplified, and I hope you cut me some slack with that, which I usually give an introduction to chemistry students who never heard about topological matter at all, but it helps us to bring each other on the same page. And so I put two pictures here, one of a typical semiconductor, which is silicon, and the other one of a topological crystal of a topological material that I grew in my lab. And so while the only difference you might see optically is that we have made silicons for decades, and as a crystal grower, I'm a bit embarrassed of these nice crystals and how this looks in comparison. But otherwise, optically, there's not really a big difference between these two materials. However, I mean, I don't need to tell you this, but just to bring us to the same page, there's of course an electronic difference, whereas a typical semiconductor, and here I grew it like as an example of an organic semiconductor, would have a band gap between a pi and a pi star band. A topological material, which can be a semi-metal or semiconductor, will have a band inversion where the band character switches, and then this band inversion of course causes surface states and something else. And I just want to make sure that for the remainder of this talk, when I define this, is that I view topological materials as like a band inversion as being the basis for this, because spin orbit coupling can come in later to gap out states and define a topological invariance. But if you have a band inversion, that's the first easy ingredient for a material to be topological. So I will be looking from a chemical perspective about what can we do or make to design materials to have a band inversion. And so just how are topological materials predicted? Well, so far, the early materials we found by educated guesses of materials. And since then, there has been immense effort, and I think you heard about it from the last speakers, of classifying all known compounds which are listed in databases like the Inorganic Crystal Structure Database, based on DFT and group theory, to classify if they are topological or not. And while I really appreciate this effort, and I don't want to talk down it in any sense, as a chemist, I just have this little thing that bugs me with this, is that I need a guideline or a heuristic or a rule for something, because that's what we chemists are built on. We have these kind of rules that we call, for example, arrow pushing when we draw organic reactions, where we know how electrons flows, and based on these rules, we set up whole industries like the pharmaceutical industry. And so my goal is to build chemical heuristics or kind of rules, guidelines that help us to predict when a material can be topological, or how to design a new one without having to run DFT calculations to test these. And so in order to understand this, I want to bring us on the same page about how we discuss electronic structure, because this is actually, I find, the biggest gap in language, actually not for me to talk to a physics audience, but rather to talk to my students who are chemists. Because if like a physicist, if I would ask you to define an electronic structure, you would give me some variant of, it's the momentum-dependent energy of electrons, and you can get it from the Hamiltonian. But if I talk to my first-year chemistry students, they don't want to talk about their Hamiltonians unless they were quantum chemists. And they rather want to have anything that they can visualize. Chemists are very visual scientists, and so they think about orbitals because you can draw a picture of them and then understand a lot about chemical reactions. But there is actually a very nice or elegant way which was introduced by Roald Hoffmann in the 80s, which lets chemists keep drawing pictures to derive electronic structures. And I want to explain that to you on the basis of a 1D chain of hydrogen atoms in the Piers distortion, just because this basis is actually everything that allows me to define rules for topological matters later on in this talk. And so you can write, this is, chemists call it the LCAO approach, which stands for linear combination of atomic orbitals, kind of like a tight binding Hamiltonian. You can write this in periodic boundary condition, you get an equation like this. And then if you write this out as a gamma point, where k is 0, you will get a sum of orbitals with the same phase, and you can draw them as pictures in the same color. And if you put this sorry, I just got an email, it's really loud in my headphones. Anyways, so if you draw this in the opposite, on the Brillouin zone boundary, you will have alternating signs of orbitals. And so chemists would call this arrangement right here as being very anti-bonding, whereas the arrangement here at gamma is being fully bonding. So the bonding states always need to be lower in energy when the anti-bonding states, which lets us draw a band like this, which is half-filled in the case of hydrogen. But then if we consider hydrogen atoms, chemists intuitively know that there are actually 2 atoms per unit cell, not 1, as I draw here. So if we extend the unit cell, then we have to extend the models, and we have to put a fully bonding, anti-bonding version at the gamma point, just like we would do in an MO diagram. And that results in this folded version of a band structure here, where we have a degenerate point here with alternating white and black spheres. And then the moment we form a bond between the hydrogen atoms, we shorten the distance. And so this is why I'm highlighting how chemical bonds become important. So this is the step where we form the chemical bond and we change the distances between the atoms, which will open the band gap here, which is obviously the Piers distortion. Okay, so this is the first thing, is like if we have a half-filled band with 2 atoms per unit cell, the formation of a chemical bond will cause an insulating state. And so this is actually relevant if you want to understand graphene from a chemical perspective. Because if you look at graphene chemically, we can describe this as a carbon atom with 3 regular bonds, sp2 hybridized bonds, and then 1 half-filled pz orbital where we have 1 electron left. And so if you draw this in a chemistry band structure, we have a filled sp2 band and a half-filled pz band. And then let's kind of extract this into k-space. I'm ignoring any kind of symmetry here. So this would result in a half-filled pz band. Okay, so this band structure, while it explains to us intuitively why graphene should be metallic, it does not show a Dirac cone and does not really give us any idea about the topological physics yet. However, when we look at graphene's crystal structure and understand that it contains 2 atoms per unit cell, we could use Roald Hoffmann's logic and say, okay, 2 atoms per unit cell means we have to fold the band structure, just like here. And since this is the anti-bonding part of the band, this would be the pi part of the band and the pi star part of the band. And then if we extend drawing the band structure to the next Brillouin zone, we would get this band structure with an inversion between pi and pi star. Of course, this is a very qualitative, I don't even want to call it model, let's say argument, but I think it qualitatively describes the band structure of graphene. so the interesting step is that here in this slide, we stop at the state where we doubled the unit cell, and we don't follow the last step, which we described in the Pius distortion model, where we form a chemical bond to open up a band gap. Because if we were to do this, like I drew here, we would just open a trivial band gap. Or if we do any other thing to localize the electrons, like we put different atoms here, like we just go one to the left and the right in a periodic table, we open a trivial gap. Or if we add a fourth atom, buckle the whole thing, we also open a trivial gap. The reason why graphene does not distort and does not open a gap is that the electrons are delocalized in this orbitals. And so we often draw this in chemistry with drawing these rings to indicate the delocalization. And so this delocalization from a chemist perspective is the reason why graphene has a Dirac cone, because that is what protects the material to be symmetric, to have the 6-fold symmetry. So if you would say it's the C6 symmetry that protects the Dirac cone, I mean, I say it's the same thing. I'm just saying electron delocalization is what protects the C6 symmetry in this material. So that made me understand at some point that I want to look and find more of these delocalized bonds in materials to this way design topological materials. So I went back to Chemistry 101, thinking about what do I know about chemical bonds that are delocalized and how can I have them in systems. So we know that we can have ionic bonds like in sodium chloride, and then that these materials have a strong, have usually a trivial band gap. They're salts, they're large insulators. We can also have covalent bonds, and we call that these regular covalent bonds 2 electron true center bonds. That means 2 electrons just bond 2 atoms together. And these covalent bonds usually also cause normal band gaps. So this is, for example, the structure of diamond or silicon boron here. And then we have these delocalized bonds, like we have them in graphene. And in the beginning, when I was thinking about it, I thought, okay, I'm a bit screwed because these delocalized bonds are something which is very special to carbon. So we know that carbon can form these what are called conjugated bonds. And that's why organic chemistry is such a big field, and humans are made out of carbon because it can bond to itself and make all these special bonds. But other elements don't really do that. And there have been Nobel Prizes in chemistry given for small molecules where they could do this on a very, very slow scale, have them behave like carbon. But having this in a 1D solid is extremely challenging. So for some point I was stuck at this, but then I realized that I formulated this as being a 2 electron 2 center bond. And I realized that at some point in more advanced inorganic chemistry classes, I learned about these 2 electron 3 center bonds or 2 electron 4 center bonds. So what are these? These kind of bonds, they can appear in molecules where I don't have enough electrons to fulfill the golden rule of chemistry, which means I always have to count to 8, and every atom wants to have 8 electrons around it. So let's consider a HYPO, what's called a hypervalent molecule like BH3, where I have only 6 electrons around the boron. And so because it has only 6, not 8, it's unhappy and wants to form another bond as indicated here to be happy, but there are no electrons to form this bond between 2 molecules. So what it does instead, it forms a bond bridged through hydrogen atoms, like shown here, and it forms these so-called banana bonds, which have 2 electrons distributed over 3 centers, which is why they're called 2 electron 3 center bonds. So here I have some electron delocalization, but only within a molecular scale. So I want to find these bonds, of course, in an extended 1D solid, at least 1D, to have a topological material. So we can also have these bonds in what is called hypervalent bonds, where I have too many electrons. Like, and one example is PF5, we have 10 electrons around the phosphorus. 10 is too much, more than 8. And so what it does is it delocalizes 4 of these electrons over these 3 centers here, forming a 4 electron 3 center bond. So again, we have some local electron delocalization in the system. So the big question is, can we have these bonds not only in molecules, can we have them in extended solids? And actually, Roald Hoffmann again already found out in 2000 that we can have these bonds in solids, because he found materials where you have antimony chains with 7 electrons per atom, or antimony square nets with 6 electrons per atom. And he classified these compounds as hypervalent. So let me explain to you why they're hypervalent. Let's look at the square net of antimony. This has 4 bonds, but each antimony has 6 electrons. So this adds up to way too many electrons, 10 again to be precise, for the antimony. So it's the same case as we had in the phosphorus fluorine molecule earlier. So what a compound with 6 electrons, or an atom with 6 electrons would want to do, it would like to form zigzag chains here, so that it has 6 electrons plus 2 bonds, which adds up to 8 again. So sulfur, the element sulfur, does that. But here we have a square net, so it's not ideal, so it must be hypervalently bonded. And basically, again, we have something on a bridge of a Pierce distortion, because we would expect it to distort this way to form zigzag chains. Kind of like chemically, we would expect graphene to want to distort, but it doesn't. It does not distort, so it maintains the symmetric higher symmetry states due to electron delocalization. And so can we have this in real materials? And yes, the answer is yes, we can. We can, for example, look at this compound, zirconium silicon sulfide, where we have such a silicon square net, also with 6 electron per silicon in the material. And so this compound, I already studied this some time ago, has shown to have this really beautiful, large linear dispersed bands and band crossings. Sorry. And what is remarkable about this band structure is that the energy range in these bands are linear dispersed is very large. So graphene, of course, has a larger range of energy dispersion, but most other real materials don't. And so these are crossing a bit more often in the Brilliant zone than in graphene. This is because it's a square net structure and not a honeycomb. And so this will result in a nodal line rather than direct point nodes in the Brilliant zone. But you can measure ARPIS, and you see the same linear resolved dispersed bands in ARPIS, in addition to some surface states which are very intense here, which are not important to the story. And you can do transport and optical measurements. And so these are just some example papers that came out showing that this has indeed the electronic properties that would resemble such a band structure. So what I wanted to understand, however, is the question is how does the square net lead to this band structure, and can I understand this chemically in some sense? So I can make the Roald-Hoffmann approach. You can do this and write down the orbitals, and then see the energy dispersion of orbitals of S and P orbitals in a square net, and I would get a band structure like this. If I plug it into a tight binding model, and actually we created this figure with a tight binding model, you get the same result. The problem of this model was I did not see any of this dispersed linear band crossings, so that didn't really explain how the square net could do that. But then if you look at the crystal structure of zirconium silicon sulfide, you will see that the silicon square net, which is the one we care about, actually has a side-centered unit cell. So it has 2 atoms per unit cell, which means, again, we have to fold the Brilliant zone to understand our band structure. So if we fold it accordingly, we get these nice dispersed PX and PY bands crossing like in a band structure. And if we, oh, sorry, I forgot something. Yeah, so and the height of the PZ bands and S bands here are completely arbitrary set. That could be somewhere else. But the PX and PY bands have to cross the moment I fold the Brilliant zone. So, okay, so now I could think about all I need is 2 atoms per unit cell, because band folding seems to be the trick. So why do I care about chemical bonding? Well, so what band folding does is that it creates these crossings, or also these points at the Brilliant zone boundaries, as has been discussed by Young and Kane and other people, but it does not put my Fermi level on the right place. So if I just have 2 atoms per unit cell, I would have my Fermi level maybe up here, maybe down there, maybe over there in space, who knows where. But if I combine this with the condition for the electron count of a chemically delocalized bond, of a hypervalent bond, then my Fermi level will be automatically pinned at this position where the band crossing is. And so we can write actually a little bit better of a tight binding model. This was done by Jan Cano. where you include some next nearest neighbor interaction in the square net lattice, and you get a band structure which is remarkably similar to the DFT band structure and also the ARPIS band structure. And so just I want to say is really this is just a tight binding model of px and py orbitals, and it really nicely describes this system. But what I wanted to understand is how can we use this knowledge that delocalized chemical bonds can lead to these beautiful band structures to find more of these materials. Because now we can go to the database and look at all the 500 isostructure compounds in this materials, and we can make a periodic table, color code which element can sit there where, and we see we have a gigantic variety of compounds available. But not all of them will have the Fermi level at the right place. All of them will have two atoms per unit cell in the square net, but not all of them will show the band structure we want to. And so, of course, we could argue that we just need to count the electrons to know where the Fermi level is. However, for this, we need to know about oxidation states, and these can be very ambiguous in very intermetallic compounds. So just a simple electron counting is not necessarily a good tool to filter out the good materials based on the ones which are not interesting. And so what we did instead is we put up this hypothesis that if it's really a chemical bond which is responsible for these beautiful linear dispersed bands, then the atomic distance between these atoms in this densely packed square net needs to be shorter than the distance to the next atom above and below, because a chemical bond always reduces distances between atoms. You could also view it as like, if I want my tight binding model to describe the square net here perfectly, then it's better isolated from all the other junk in the crystal structure. So we defined a distance ratio where we said this distance here needs to be shorter than this distance or this distance, whatever here is the shortest. And so you can write a formula based on this. This is just based on lattice constants and Rykov coordinates, which just gives you a geometric, what we call tolerance factor, to when we believe, based on our hypothesis, we should have band inversions in these materials and at the Fermi level, and when we should not. And so we could say it should be smaller 1, but actually we found later that like giving it a bit of leeway and saying smaller than 0.95 is a better method. So let's see how that works out. So we can make a plot. Here we put the distance inside the square net on one axis and the distance to the next nearest neighbor. Oh, this is the square net distance, this is the next nearest neighbor on the other axis, and which makes it all compounds which fall in this yellow area are the compounds where we expect band inversions to appear, and all compounds up here in the blue area are compounds where we don't. And then the green area here is kind of the gray area where we don't really know what happens. Our method's not good enough. And so the colors here represents electron counts, if we can count. The gray ones are ones where we cannot count electrons. And so now we can take advantage of Andrew's beautiful database and just look up the DFT band structures of those that are available and see if our methods make any sense. And so what we found is that all the compounds up here show band, nearly all of them show band gaps and just are trivial semiconductors, very ionic compounds, whereas here fall all these compounds which are already known to be topological semimetals and published. They all fall in this area. And also I want to highlight this compound, uranium ditelluride, where it's slightly, there is a different structure of polymorph, but still chemically related, is now researched as a candidate for topological superconductivity. And so this is a highly correlated material, and it falls in our plot in the correct region where DFT would have issues due to the correlated nature of this material. Okay, so this plot was awesome because it showed us we can predict materials, but sadly, the materials we found through these things weren't new. People already discovered these, and we couldn't present any new types of topological semimetals we found with this method. However, the nice thing about solid-state chemistry is now that we established a structural motif of a square net to be of interest for a certain property, aka band inversions or topological semimetals, we can extend or try to extend this to other crystal structures where we have the same structural motif. That's something very common done in solid state chemistry, where a structural motif is linked to some kind of property appearance. Think about iron arsenide superconductors, where everybody was focused on iron arsenide tetrahedra. And once we have this structural motif established, we use this to find more materials with the same properties. So here, just some example of other crystal structures that show this motif. And I want to highlight this structure type for now, because here we make the same plot, we do find a lot of more materials. And so in this plot, the colors mean something different than in the previous plot, because now we put all the materials in green, where the band structure published on the topological quantum chemistry websites follows the square net tight binding model roughly. So all these green materials are here in the yellow regions. And then all the red materials have a band gap on topologicalquantumchemistry.com. And all the blue ones, they are a metal on topologicalquantumchemistry.com. But if you Google this compound name with band gap, you find an experimentally determined band gap. So these materials are known to be semiconductors or insulators, but DFT does not give the right result for them. And then we have this orange guy here, where it is a metal in the database, but we did not find information about the band gap in the literature. It is, however, an electron precise material, how we call it. So it should not have delocalized chemical bonds, and we would chemically expect it to have a band gap, but we can't say for sure. Anyways, what is important are all these gray materials, which do not appear in a topological material database, but they do appear in the ICSD, and they don't appear because most of them are some kind of alloys where you have disorder, as you can see here. So it's hard to do a DFT high throughput calculation on these. And so we picked out one of these candidates, which falls in a yellow area, which is not too crazy disordered, to model this ourselves to see what we get. So this was done by a visiting graduate student from UCSB to our group, Sam Teicher. And this is the crystal structure of the material we're looking at, where the zinc atoms are only halfly occupied. And so he constructed two different types of supercells to model these vacancies and disorders. And then he calculated the band structure, and then he also unfolded the band structure again so that it's shown in the Brillouin zone of this subcell. And so this is the band structure you get. And while you see you have smearing here from the disorder, these linear dispersed bands, which are the ones we care about, appear clearly in the band structure and are less smeared out from the disorder than the other ones, because they stem from the antimony square net, which is the hypervalently bonded square net. So this gave us some confidence that we can accurately predict these materials based on a tolerance factor, even before doing any kind of DFT calculation. And so I gave this talk actually also at Aspen in January, and then someone from the audience pointed out that they made similar materials in the vacancy ordered, and it was an insulator. So we quickly grew crystals to make sure it's not an insulator, and we did this, and in our case, we find the metallic resistivity of this material. So we are confident in this prediction. So then the last thing I want to talk about, if I have a few more minutes, is this crystal structure. Oh yeah, see, I'm going to go a little bit quicker to this last talk, because I see I'm running low on time. But I got interested in this type of crystal structure with square nets, because this is a structure where I have two square nets on top of each other, which doesn't appear in all these other structures. And so here I expect the layers to be bonded very weakly to each other, so I can scotch tape and create a 2D material which connects to my other research interests in the group. And I also like that this contains rare earths, which gives me the opportunity to add magnetism to compounds. So I was hoping that these can be materials which behave similar like topological materials that have, let's say they have high electronic mobilities, but also have magnetic order and can be exfoliated. And so if you plot these materials, so there are two types, even more complex crystal structure here. But if you plot these on our plot, these all fall into our region of interest for hypervalent bonds. I want to point out that I did not invent these materials. These has been studied before by Ian Fisher and Mercury Kanatzidis, because they are known to undergo charge density waves, which result in very complex modulations around room temperature. And so the fact that they undergo charge density wave kind of discouraged me at the beginning, because my argument is built on this square net not distorting to have a hypervalent bond. However, the structures they reported from the charge density waves were so complex that you could still not describe these nets with 2 electron 2 center bonds. So there should still be some hypervalency left in these materials. However, if you now look at the band structure of these materials, they have 6.5 electrons per square net. So the Fermi level is higher than these. And this is before charge density wave and without any magnetism. And it's a mess of a band structure. So I like to point this out, that if you go for a database and see this band structure, you might not deem this material too interesting. However, if you think about it from a chemical logic, that there should be some hypervalency in these bonds at the Fermi level, you might have a second look at this material. So yeah, so we looked at this material, we grew crystals. I'm going to go through this quickly. We checked that they're still metallic even after the charge density wave. Charge density wave comes in here. Crystals are metallic. They have really high RRR ratios, which means that the crystal quality is high. They do order antiferromagnetically below 12 Kelvin and actually have 3 different magnetic ordering temperatures. And if you put them in a magnetic field, they display very beautiful quantum oscillations. And this is a first indication that they should have high mobility. The second indication was that we measured Hall effect, where we measured very high mobilities at low temperatures here. And so this was the first mobilities we measured of 30,000 centimeters square per Wall second. But then my postdoc wanted to higher the crystal quality, so he grew even better crystals with RRRs of over 900. And here, depending if you fit Hall resistivity or conductivity, you get mobilities of 100,000 to 60,000 centimeters squared per Volt second. So this is extremely high. To give you some context, the only other layered material we found which surpasses this is graphite. Black phosphorus is about the same. Nothing that has any kind of magnetism or magnetic order is known to have this high mobilities and temperatures where there's magnetic order. And so I strongly believe that this is related to hypervalent bonds on the square net. Last thing, we also proved that we can exfoliate this material. Let me skip through this. So you can exfoliate this to monolayers and you can try to make contacts. The problem is that these materials are so air sensitive and monolayers limit that these devices keep dying on us before we get monolayer data. However, I'm optimistic we can improve this in the future. This is not part 1 of my talk. I just forgot to remove the part 1. This is the end. So let me summarize what I talked about. So I hope I could convince you that chemical rules can be extremely useful and can be defined to find topological semimetals, at least in materials with a certain structural motif. And in principle, it's not impossible that these rules can be extended to other materials also. And that after we found these rules, we could use them to identify more materials. And most importantly, we could use them to find the first material which is exfoliatable, but also has a high mobility and magnetic order. With this, I would like to thank you for your attention, and as well as my group and collaborators. Thank you.
Thank you, Leslie. We could take one question. Antoine?
Leslie, can you hear me?
Yes.
Okay, so that was a beautiful talk, and you certainly illustrated the powerful character of chemical rules. But you also contrasted this to systematic searches using electronic structure methods and DFT.
Mm-hmm.
Two kind of approaches we made to work together, actually. Can you import some of the chemical rules to
I think so, because I think these approaches can basically serve as a pre-filter to look at compounds which we don't need to bother with, and then give us fewer compounds where we can look with more expensive DFT and therefore like ramp up the calculation efforts, or even look with DMFT or other methods because we can single out fewer materials.
Can you
give other examples where these chemical rules have been useful, like ferromagnetism, anti-ferromagnetism, superconductivity, etc.?
Sorry, I did not fully get it. Could you repeat it?
The question was whether there are other situations where instead you're looking for superconductivity, anti-ferromagnetism, et cetera, rather than topology where these sorts of rules can be useful.
Yeah, I mean, so the delocalized bond rule is definitely completely linked to band inversion or linear bands, but there are lots of chemical guidelines to find superconductors based on structural motifs and things which are different from the ones I introduced right now. But in principle, that's what Bob Carver has been doing his whole life. So that's definitely a thing.
Okay, thank you, Leslie.
Thank you.